Okay, we'll get started then. Are you guys able to see this okay? I don't know how to adjust the lights in this room. It's usually you hit a button and it'll turn off the front row of lights, but let me try again. Usually it's this button. But it doesn't, is it doing anything? No, this is just turning off the whole room. I don't know. Is this better? Okay, all right. Just don't fall asleep on me. Okay, so we'll do that. And then, so today we are doing, what's going on here? Chapter 3, Linear Regression. And I think you've taken an entire quarter of linear regression already, right? 101A. And I'm hoping you remember most of it, but just in case, we'll spend today reviewing it. And I know I said I would get homework, your first homework assignment posted, but I wasn't feeling great yesterday. I just ended up spending the whole day sleeping, which was actually really wonderful, but but I didn't get any work done. And so, so I didn't finish the homework, and I only got halfway through today's lecture slides prepared. And then I'm going on a trip this weekend, so, you know, anyway, we'll see what's happening. Okay, but anyway, linear regression, I'll get your homework posted. First homework assignment, it'll be out of chapters 2 and 3, just the exercises straight out of the book. And again, you know, do your best working through them on your own. Try not to peek at the answers that you might find online and stuff. Okay. Anyway, so we'll take a look at this advertising data set. And the advertising data set measures the output variable is sales, okay? And that's measured in thousands of dollars. And then as far as predicting the sales, we're looking at you know, how much money was spent on TV advertising, how much money was spent on radio advertising, and how much money was spent on newspaper advertising, and we want to know what's the relationship between money spent on advertising and sales. And you know, I know a lot of us like to think that, well, I don't know, that advertising doesn't affect us, but it totally does. Like, it's definitely shown that if you spend more on advertising, you're gonna sell more stuff, right? And because you think like, why would people spend money on like Facebook ads and stuff? But it works. Okay. And so anyway, here's just a plot of like some of these things and what we see, and so we can see, you know, as more money is spent on TV advertising, then the sales go up. As more money is spent on radio ads, sales tend to go up. Newspaper ads, I mean, there's also a positive trend there, although it's a little bit more scattered, and we want to come up with some kind of relationship between all of this. And we have, you know, different questions that we might have, and these can all be answered with linear regression. Linear regression is a simple approach. And you know, we covered earlier on, and you've already had a course on it. But it's very powerful and it's very interpretable, and so we can answer a lot of these kinds of questions. You know, is there a relationship between you know, how much you spend on advertising and the sale? How strong is that relationship? Which of these media, TV, radio, and newspaper contribute to the sales? How accurately can we estimate these effects, or can we predict future sales? And then, you know, is there an interaction or synergy between the advertising media? These are questions that that we might be interested in, and anyway, that's where we go. So we'll just start off with the simplest form. This was probably covered in your like Stats 10 class, and that is simple linear regression. And here we only have just one predictor. We just have one predictor variable x, and we're predicting a y. based on that. So we got your output variable y, your input variable x, and the model takes on a linear form, meaning it's just intercept plus slope times x, right? And this is the model. This is, we are saying that there exists some relationship out there in the population, and it's a linear relationship between these two variables, between x and y, that as we spend more money on x, we're going to get more sales, okay? Or, you know, the more whatever, you know, you increase the square footage of a home, the price of the house goes up, you know, stuff like that. There's some kind of variable relationship between x and y, and this is maybe the population relationship. There's in the population, which is, there's a true value for beta 0 and beta 1, which is unknown to us, okay? And of course, even this population relationship doesn't capture everything, and so there's still a error term, epsilon, left over. And then when we fit our model, we're just coming up with estimates of these parameters, okay? We're getting an estimate of b0, so which we'll call b0 hat, and an estimate of beta 1, which we'll call beta 1 hat. Some textbooks will use the Latin letters, so instead of beta 0 for the parameter, and here instead of beta 0 hat, we'll have b0 rather than beta 0. But our textbook uses beta 0 hat. It's fine. And the way we choose to estimate these coefficients is we're going to use the least squares criterion. So we're going to say, when we say, you know, if we pick a value to estimate beta 0, if we say, I'm going to choose this value for beta 0 hat and beta 1 hat, we say, somebody might say, you know, the slope should be 2 and the intercept should be 1. And someone else says, no, 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 the slope should be 3 and the intercept should be 2. Well, how do you decide which one does a better job? Okay, well, we decide which one does a better job by looking at the total sum of squares. So we're gonna, so if there's two competing models, so I mean, this is just a silly illustration. Let me just fix this briefly. Okay, so, you know, you might have something like this, okay? So this might be your, whoops, this might be your data set. And you might have two competing lines, right? So one person says the line we fit should look like this, and then someone else says, no, 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 the line we fit should look like this or something, right? Okay, so which line does a better job? Well, what we do is we're going to look at the residuals for each of these things, and the residual is going to be the vertical distance between what the line predicts and what the actual value is. Okay, so we have this and we've got this. So these are the residuals. And then, and what we do is then we square each of these residuals. So the squared residual will be something like this. So we take each residual and we square them. and then we just ask, what's the total area of these squared residuals? Something like that, okay? And whichever, probably the one on the left has smaller squared residuals or something, but we say, you know, whichever line has the smallest sum of squared residuals, that's going to be the best fitting line, right? So the residuals are going to be the difference between the actual value, the yi, and the predicted value, y hat, okay? And the y hats are rest on the fitted line, and then the yi's are the actual values themselves. So in our diagram, whoops. So this is your yi, and this value on the line is your y hat sub I, okay? And then this distance here is your e sub I, and then this shaded square is going to be your e sub I squared, okay? And then we want the one with the smallest total, e sub I squared. Here it is. Here's kind of the diagram for our TV versus sales data. Okay, so this is, so my plot only had 4 dots. This has a lot more. Every single one of these vertical lines, we square those distances. Okay, and that's going to give us our residuals squared, and we sum them up. Okay, and you know, because the model is a straight line, it's only able to predict one value, okay? So even though, like, if you look at TV 200, okay, we can see there's like 1, 2, like 3, 4 values where the TV value is 200, okay? It's only able to predict the same number for all of them, okay? It's gonna predict whatever whatever's on the blue line right there. That's its prediction, that's its y hat for all 4 of these things. And so we're going to get some kind of squared residual there. And what we want to do is we want to minimize all of this, okay? And so with some calculus, we find that the slope that minimizes the squared residuals and that the intercept that minimizes the squared residuals will take on this value, okay? And if you do it in matrix notation, you get something like x transpose x inverse x transpose y or something like that. You get these different values, and I think you had to do this in 100B probably, or was it 101A? Which class? 100B, right? Okay, so you had to do this already, so I'm not going to bother wasting time. I mean, maybe today's whole lecture is a waste of time because you've already seen all of this, but we're just reviewing this, okay? And so, you know, we find out that the slope and the intercept take on these values, okay? Because we have 2 parameters, a beta 0 and a beta 1, we can actually plot out kind of the contour surface of the RSS being the residual sum of squares. So when you choose these values, beta hat 0 and beta 1 hat, okay, you're going to get the minimum value. So when beta 0 is 7.03 and beta 1 is 0.0475, the RSS, which is the sum of all of these things, is going to be at the minimum. And any other value you pick, if you pick beta 0 to be a little bit bigger than 7, like 7.2, you're not going to achieve the minimum, okay? And as beta 0 gets bigger and bigger and bigger, you get more and more farther away from the minimum. Same thing with beta 1. As beta 1 changes values, and you can see beta 1's, it's very sensitive to changes in beta 1, the values change drastically, okay? And this is also kind of a 3-dimensional plot of what this looks like, okay? What is it that I'm talking about here? I've got this app here, not this app, this web page. Okay. And so here is our data, okay? And what I can do, so this plot, let's zoom in a little bit. How do I zoom in? There we go. Okay, so this plot represents, here's our data point, and this line is our fitted line, okay? And right now it plots out the vertical distances are residual, and it makes every residual into a square. So we can see the squared residual here, this green square right here, this is a squared residual, and this brown dot has this brown square, which is very big. This purple dot is almost on the line, so it has a very tiny squared residual, and that's this tiny little purple dot here, okay? And this is fun. I can change the slope, which is going to, all it does when you change this, not the intercept, not the slope, the intercept. If I change the intercept, that basically just slides the line up and down. And we can see that if I bring the intercept like way up here, this is a terrible fit, okay? We can see we have a huge residual between the orange and the blue dot, okay? A huge residual, and so we have a huge squared residual, okay? And the sum of the squares is ridiculously large, and so as I shift this around, you know, like maybe I want to minimize the sum of the squared residuals, and we can see that because the orange and the blue are kind of on opposite sides of the line, if I shift the slope down this way, I can shrink the size of the blue square, but that's going to grow the size of the orange square. And if I try going the other way, it's going to increase the size of the blue square and shrink the size of the orange square. And what I want to try to do is I want to try to find kind of the intercept that's going to minimize basically the sum of all of these squares. All right. Same thing, and at the same time, there's two things. It's not just one knob to play with, right? So here's one, like I'm shifting the intercept. But I also have another knob, and this is the slope. And so here, right now the slope is 1, but I can make the slope flatter or more steep, okay? And we can see that as I increase the steepness of the slope, you know, we get different things. So what I want to do is I want to try to minimize the total squared residuals, which, you know, it's not easy, but you know, this seems to be doing an okay job, and I don't know, maybe that's better, I don't know, something, right? So we're trying to minimize the total squared, and we can see that choosing a different intercept has an effect. Choosing a different slope will also have an effect, and that you know, and basically what this plot shows is that, you know, someone says, okay, well let's just keep the intercept constant, all right? How does changing the slope affect it, right? So as I crank the slope higher or lower, we can see like, okay, it gets, once you start going a certain way, it gets bigger, 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 and then so now we're getting smaller, and then I've gone too far, and now they start getting bigger again, right? So that's what we're seeing here. As I'm changing the values of B1, it goes down and then it goes back up again. And then, you know, wherever I go. Same thing with beta 0. As I change the values of beta 0, they go down, but as I keep going, they start getting bigger again. Okay, so that, and that's because we're using the squared residuals as the measure, which is a quadratic thing, and you know, all the quadratics have this parabolic shape, meaning as you go from left to right or top to bottom, you know, they go down, down, down until you reach the minimum, and then they start increasing again. Okay, and so, you know, in 3D it looks something like this, and if you make a contour plot, it's going to look something like this. Okay, and you can kind of play around with, you know, this thing to kind of get an idea of just, you know, shifting that intercept up and down, how that affects the squared residuals. Changing the slope also affects the squared residuals, okay? But again, via calculus, you solved it and you said, you know, this is going to be your best fitting slope, and this is your best fitting intercept, right? Okay. Is this all okay? This is all good? Okay. And then, so anyway, you've done all this work, and you arrive at this, and you say, okay, well, this is what our best fitting line is going to be. We have the slope that's going to minimize the sum of squared residuals. We have the intercept that minimizes the sum of squared residuals. Okay, are we done? Well, as far as fitting the model, you're done. Okay, as far as just estimating the coefficients, that's fine. You've got the line, you've got the coefficient that minimizes the slope, you've got the coefficient that minimizes, you have the slope coefficient that minimizes the RSS, and you have the intercept coefficient that minimizes the RSS. So as far as that goes, you're done. But what we have to recognize is that our data is not the entire population, okay? Our data is just one possible sample out of the infinitely many samples that could have been taken from the population. Or maybe there's not infinitely many, but there's many samples that could have been drawn from the population, and we just have one sample here. And so if someone else were to go to the population and get another sample and then fit a best fitting line there, their slope and their intercept will not be exactly the same as the slope and intercept that we estimated. Okay, so when we did it, we got a slope of 0.0475 and an intercept of 7.03. If someone else gets new advertising data and TV stuff, even if it's the exact same population, okay, they're not doing anything different, it's the exact same population, they're going to get slightly different data points, and because they have slightly different data points, their intercept and their slope estimates will be slightly different from ours, right? And so this is an illustration. What this diagram is supposed to illustrate is this idea, okay? So this red line represents the true relationship between the slope and the intercept, okay? This is taken straight from the book. This red line represents the true relationship between x and y, okay? So this is the true slope and true intercept of the relationship between x and y in the population. But there's random noise, right? It's this might be the true relationship, but there's random noise, and so these dots represent one random data set generated centered around this red line. Okay, so the red line represents the true relationship, and the dots are just one random realization. And so if we fit the best fitting line to the data that we've observed, because we don't know what the population looks like, we fit the data to this blue line, this is what we get. Okay, or if we fit a blue line to the data, and this is what we get. Okay, and what we see is that the blue line looks kind of like the red line, but it's not exactly the same. Right. And so the question is, well, what if we got a different random set of data, and we fit another regression line to that, okay? What would those regression lines look like? Okay, and so in light blue over here, we've generated other random data sets that look kind of like this, but not exactly like this, and we fit regression lines to each of those. And every time we fit it, we got something slightly different. We got a blue line that goes up here, we got a blue line that goes over here, we got, you know, all of these different light blue lines, okay? And what we see is that these light blue lines, they're kind of similar, and in general, they're centered around the red line, which represents the true relationship, but they also differ from each other, and they differ from the red line as well, okay? And of course, when you are dealing with a data set, you don't know if the fitted line you got is the one that's too steep or if you got the one that's too shallow, okay? Because you don't know which ones, you don't know what the population looks like. We're always, in all of statistics, we're dealing with just a small data set, a small sample, and we're hoping that our sample is representative of the population, but we don't know what the population looks like, and so we don't know if our sample is giving us, too big of a number or too big of an estimate or too small of an estimate, and likewise, we don't know if the resulting slope we get is too steep or too shallow. We have no idea. When we fit our line, we get just this dark blue line. And what does the population look like? We don't know that the population is a little bit less steep. It's a little bit more shallow, okay? Or, somebody else, they take a sample of data and let's say they get one of these shallower blue lines, okay? And again, that's all the data that they've observed. They have no idea that their sample is producing a slope that's more shallow than what the population is. Nobody has any idea, right? So, when we do our analysis, we have to take into account this variation that exists when we fit our data. When we estimate slopes and intercepts and whatever it might be, we have to accept the fact that it's based on a random sample of data, and if we were to have a different random sample of data, we would get probably different values, and we don't know if those values that we would get would be bigger or smaller or whatever, okay? But the good thing about all of this is that, in the long run, we can expect all of these different slopes, all of these different intercepts to be centered around the true line, okay? Okay, we say that the least squares regression line is unbiased, okay? And to be unbiased means that in the long run, we expect it to be right, okay? In the long run, we don't expect our least squares regression line to overestimate or underestimate the slope. It's not going to overestimate or underestimate the intercept, okay? That if we did this process of taking a random sample, fitting a regression line, taking another random sample and fitting a regression line, and we take another random sample and fit a regression line, if we get a whole bunch of these things and we look at all of the different slope values that we fit, some of the slopes will be too steep, some of the slopes will be too shallow in comparison to the true regression line. In the long run, the average of all of those will be right, okay? And that's what it means to be unbiased. Unbiased means that in the long run, all of the estimates will be right. Yeah? You guys covered unbiased estimates in 100B as well, right? And so the sample mean is an unbiased estimate of the population mean, right? You guys learned that, okay? And what about the standard deviation? What's unbiased and what's not? Which one's biased? Or variance? Okay, how do we find the population variance? So if we have a finite population, what's the variance of your finite population? So you have a finite population, right? Maybe you guys are just too shy. So if you have a finite population and we're talking about the variance of a finite population, I guess I'll save this. I don't know if this picture's worth saving, but. All right, this is a side note. Okay, so if you have finite population, the variance, we can think of the variance as what? The average, what? Squared deviation from the mean. We know this, right? Okay. And so we would do something like, each x, and we would subtract off the mean, and we would square it, and we would add them up, and we'd divide by n, right? This is kind of the variance of x. Okay, and if we did this for a sample, the sample variance, if we just did the same thing, what would happen here? This turns out to be what? This gives us a biased estimate of the population variance. Right? Okay. And why is it going to be biased? The unbiased, how do we make it unbiased? One over n minus 1, right? 1 over n minus 1, unbiased estimate. Okay, and this means if we do this, in the long run, this estimate, S, is that kind of your expected value of S is equal to sigma, right? I guess S squared. You don't have to write all of this down. This is review of 100B. Why is this unbiased and the other one's biased? Like, is there something I could do to this to make it unbiased? Can I replace one of this? Like, if I replace this with what symbol will it become unbiased? Mu, right? So if I knew what mu is, then this becomes unbiased, right? And the reason why this is unbiased is because here what we're asking is, what's the deviation from the mean? And over here, we're saying our estimate of the mean is our sample mean, okay? Which is, of course, going to be in the middle of our current sample, right? Which might not be the same as the population mean. And so, so we're going to end up kind of underestimating the deviation from the mean, right? Because in our sample, I'm going to say, oh, the mean of the mean is right here in the middle, so of course we're going to have a smaller distance. But if the population mean is something else, the deviations from that location will be larger in general. So anyway, but what we're saying is that the least squares regression thing, when we do this, your beta zeros and your beta ones, your intercepts and your slopes, and all of your coefficient estimates are unbiased. In the long run, you're not going to get slopes that overestimate or underestimate. You're not going to get intercepts that overestimate or underestimate, okay? Which is often a desirable property, okay? But later on, we'll learn, maybe we would actually rather have slightly biased estimates to have maybe other desirable properties, okay? So, and this comes later, but I'll just kind of plant this seed in your head, is that, these estimates, these coefficient estimates experience a large amount of variance, okay? Especially when you have high collinearity in your predictors and things like that. And so, as far as unbiased estimators go, the least squares estimates these are the best that you can get. You're not going to get better estimates than the least squares estimates if you are adamant about having unbiased estimates in terms of like minimizing the variance. But you still have quite a bit of variance, and so if you want less variance in your estimates, then you could start introducing, biased versions of your estimators and things like that. Okay, so anyway, I think this is just summarize what I've been blabbing on about, saying that in the long run, okay, if we fit all of these different blue lines, in the long run, the average, if I were to average all of these blue lines together, we're going to get the true line, the red line. Okay. So, whoops, okay, I got to fix that. All right, so we recognize that our estimates of beta 0 and beta 1 are based on a random sample of data that we've got, okay? So we estimated the slope, we've estimated the intercept based on a random sample of data, and that if we were to get a different random sample of data, we would get different beta 0s and beta 1s, and if we were to do this many, many times and keep track of all of the beta 0s and beta 1s, we would have a distribution of different beta 0s and beta 1s, right? So this would be the sampling distribution of, oh, these should be beta 0 hat and beta 1 hat, okay? Sampling distributions, put little hats on here, okay? And the standard deviation of the sampling distribution is called the standard error, right? This is like review of stats 10, but at the same time, I don't know if all of you took stats 10 here at UCLA. You might have taken like intro stats in high school or AP stats in high school. And I think AP stats is a great curriculum, but at the same time, not every high school teaches it well. So I don't know, okay? So anyway, we know what a sampling distribution is, and the standard deviation of a sampling distribution is called the standard error, right? Okay, and so anytime you have a statistic based on a sample, that statistic has a sampling distribution, right? So whatever statistic it is that you're calculating, whether it's your beta 0 or your beta 1 or your t or your your r squared value, these are all statistics that are based on some sample. Every single one of those has a sampling distribution. And if you want to know the standard deviation of that sampling distribution, that's the standard error. And again, I didn't bother doing the math. Did you guys have to figure out the standard error calculations in your 100B class as well? Okay, so I think we have somewhere, at least somebody has at least shown it to you, and whether you've internalized the relationships or not is, I guess, a different concept. But I guess I just say this so you trust me rather than me just saying like, oh, look, believe me. But somebody has proven it to you, right? Probably Christo. Okay, so anyway, so we've got this, and so this is the standard error, and okay, and this is all impossible to read, and so we assume that sigma squared is the variance of kind of the noise that we're adding to our model, that it's uncorrelated, and if we look back at this plot, we can see that's not really true. Definitely the variance grows as the advertising money grows. Okay, so our assumption is violated already. And this is our life, is that you say, well, I'm going to make this assumption even though it's probably not right, okay, or even though I know it's not right, okay. The life of the statistician, because because making assumptions make your life easier. It can get you in trouble, but in general, making some assumptions about what you can expect does make your life easier, for all, basically for all of life, right? Because, you know, when you meet somebody, it's nice to go in with an open mind and say, I don't know anybody, and we'll learn all about this person. But usually you can make assumptions and say, well, I saw this person treat the waiter poorly. I'm going to assume a whole bunch of other stuff about their life, and I'm going to make my life easier by saying, well, this person is not nice to the waiter, so I'm making judgments about their personality. They're all assumptions, right? And therefore, I'm not going to invest much time and energy and effort into cultivating a friendship with this person, okay? I don't know why I went off on that tangent, but all to say, you know, in our data set, maybe we recognize that this assumption might not be a good one, okay? That we don't have constant variance in our data, but we can say, well, you know what, let's just kind of make this assumption anyway, and hope that it simplifies our life, and we can just kind of stick with these standard error estimates and continue on in our analysis. Because who has the time to really get to know a person fully, even though we saw only one interaction between this person and one other person? It was enough for us to create a judgment about their life. And similarly, we might say, you know, this might not be the best assumption to make, but we'll go ahead and keep our analysis easier. Okay. I do want to say something. If we look at the standard error of beta 1, if we look at the denominator, what goes in the denominator, right? It's the sum of squared distances from the mean. And what this means is that if you've got xi's very spread out, your denominator is going to be huge, right? And so, and that means your standard error is going to be a lot smaller, right? And so here, the idea is, so we said the standard error of beta 1 hat is equal to, what is it? Sigma squared over the sum of xi minus x bar squared, okay? So if you only have a few dots here, and you're trying to estimate the slope, okay? Maybe you get this, but other possible values, like there's quite a, maybe not that, but there's like quite a wide range of possible slopes that could be formed if you only have data in a small range. Yeah? But on the other hand, okay, if you've got something like this, okay, we'll just stick with 4 data points because that's what I used in the other thing. As far as like possible values for the slope, really, you're not going to have much variation, okay, as far as what possible slopes it can be. So you've got, so if you've got a much broader range of values, you got less variation in the slope, okay? Okay. we'll say x is confined to kind of a small region, leads to large variation in slope. Okay, or so we might say we have more leverage to estimate the slope. Okay, so that's a nice feature there. Similarly, we can make confidence intervals. Now that we have a standard error, we can create a confidence interval for the slope or for the intercept. Okay, so you can just say plus or minus 2 standard errors is going to give you kind of roughly your 95% confidence interval. Okay, and of course it's not exactly 2. It's, you know, whatever you look up in the t distribution with the appropriate degrees of freedom. Okay, but roughly 2. And as we know, if the confidence interval includes 0, what does that mean? If the confidence interval for the slope includes 0, that means, yeah, you don't reject the null. Well, I mean, technically it's not you're not doing a hypothesis test. Okay, so if the confidence interval includes 0, it means 0 is a plausible value for the slope, meaning that the slope that you observe in your data is not necessarily different from 0. That there could be, it's possible that the population has no relationship between x and y, and that just by coincidence you're getting what looks like a positive slope, right? You're getting something that looks like a positive slope. So so, you know, one example I like to do all right, so if x is 1, 2, 3, and 4, and y is 2, 6, 4, and 8, okay? And if I plot x and y, let's go ahead and do aspect ratio equals 1. You know what? Okay, and then let's do model 1 is linear model of y as explained by x, and we'll AB line model 1, color equals red. Okay. Okay. This is, okay, so this is kind of our, I've got 4 data points here, and I get this regression line, okay? The summary of this says, actually, let me not. Okay, the coefficient, the intercept is 1 and the slope is 1.6, and the correlation between x and y is 0.8. Okay. Do you guys think the slope is significantly different from 0? What's your gut instinct here? It feels that way, right? It feels that way, right? I got x being 1, 2, 3, 4, and y is 2, 6, 4, 8. Okay, and it looks like this. Okay, It turns out though, let me go ahead and do the summary, okay? If I do summary of our model, look at our p-value on the slope. So the slope is 1.6, our standard error is 0.8485, and the t is 1.886. So we could actually go back and do the calculation for the standard error on this. Sigma squared divided by all of this. R does it for us, so we don't have to do it by hand, okay? And we get a p-value of 0.2, okay? Which, by all accounts, we would say is larger than our alpha, assuming we're using alpha 5% and, you know, or something smaller, right? And so, because this has a, basically it's saying, you know, the slope that we're estimating, 1.6, could just be a result of random chance. That could happen about 20% of the time by random chance, okay? And so, so what does that mean? It basically means that if you blindfolded someone, gave them 4 darts, and they threw them at the wall, okay, then there's a 20% chance that those darts form a pattern where the correlation is around 0.8. Okay, that's going to happen 20% of the time, which makes sense. With only 4 darts, we could kind of imagine something like that happening, right? If you had 10 darts and you get a correlation of 0.8, then that's like for sure there's some kind of correlation there, okay? But with 4 darts, we could imagine something like this, right? And in fact, how many degrees of freedom do we have on this thing? There's actually only 2 degrees of freedom, right? So with 4 darts, there's only 2 degrees of freedom. Why are we taking away 2 degrees of freedom? What? Oh, because you have 2 things to estimate, right? A slope and an intercept. But even easier, two dots define a line, right? So if you blindfolded someone and you gave them 2 darts to throw at the wall, they will always have 100% correlation, right? They will always form an exact straight line with 100% correlation. So it's only until you introduce the 3rd dart can you start to see if there is any kind of statistical significance there, okay? And then so with 4 darts, you only just have to kind of get lucky enough, and you'll get lucky enough 20% of the time where you're going to get correlation around 80% of the time, okay? A correlation of around 0.8. And that's going to happen about 20% of the time. You know, which always feels a little bit surprising, because when you hear a correlation of 0.8, you feel like, oh, that's got to be like a fairly strong relationship. But with only 4 darts, it's actually, or 4 randomly selected points, it's actually quite easy to get something like that. So, so yeah, we do statistical tests, and we can say, you know, something like this will happen by random chance with a probability of around 0.2. Okay, so that's the confidence interval. That's your hypothesis test. You know, if your null hypothesis is that your slope parameter is 0, that there's no relationship between x and y in the population, the alternative is that there is. You do some kind of hypothesis test with a t-statistic, and we would say that, you know, we did not reject the null, and we don't have evidence that the slope is significantly different from 0, or we do reject it and we say that we have evidence that the slope is different from 0 and that there is a relationship between x and y. Okay. All right, so far okay? All right, this is where I ran out of time. Okay, and so here we can actually, so I'm going to just kind of go through the textbook here, and I think that's okay. So, you know, we can look at the actual data, okay, the advertising data, and if we fit the advertising data, maybe I'll make my screen bigger. Here. Okay, and we saw the plot for the advertising data in that okay, so when you plot this, I've got advertising $TV and advertising $sales. Okay, so this is kind of the plot here. We fit a regression model. We get the intercept. So we have these ridiculously huge t-values. Okay, so rule of thumb is that t's greater than 2 are significant, and here we're at 15 and 17. And so we get p-values that are practically 0. Okay, and so we get, you know, our slope of 0.0475 is significantly different from 0, and our intercept of 7.03 is significantly different from 0. We've got we have a few values, right? The residual standard error. So this is kind of our we can kind of think of this as the estimate of the so to get the residual standard error, we're taking the residual sum of squares and we're dividing it basically by how many residuals we have, but we adjust for it, so we divide by n minus 2 and we take the square root. So it's kind of like the standard deviation of the residuals, basically, is what we can write there. And so the RSE is given by this formula. Okay, so it's residual sum of squares. So that's just the sum of all of these when we fit one of these plots back here where we have the vertical line to the residuals. You know, we took all of those squares, the sum of those squares, and we're dividing that by n minus 2, adjusting for our degrees of freedom, and we take the square root. So it's kind of like the standard deviation of the residuals. Okay, and that gives us a sense of basically how much the sales will deviate from the regression line. Okay, so if I do AB line, what did I call it? I called it model. Okay, so AB line model, and we'll do color equals red. Maybe I'll do blue. Okay. Okay, so on average, on average, the dots deviate from this in the realm of around 3.259, and this is measured in thousands of dollars. Okay, so sometimes it's bigger, sometimes it's lower. Standard deviation is kind of like your typical amount of deviation. Okay, and so that's what we've got there. The so the residual standard error is you know, the RSE is 3.259, and then on the other hand we have the R squared value. Okay, so the R squared value is 0.6119. Okay, and to calculate the R squared value, how do we calculate that? That is given by this value, TSS minus RSS divided by TSS. Okay, so what does that even mean? Okay, this is the total sum of squares minus the residual sum of squares. I think this is easier illustrated with my fake data set. Okay, so how do I do this? AB line H equals mean of Y. Color equals blue. Copy this plot. Come up here. Does this work? Okay, export, copy to clipboard, copy plot. I want to paste this right here. Huh, okay. It's not working. All right, let me try again. Snipping tool. And then we just copy this like this. There we go. Okay, so here my X and my Y go like this. I've got 1, 2, 3, and 4, and 2, 6, 4, and 8. Okay, and if we used no predictors, okay, then and if somebody asked us to make a prediction for Y, so if we're using no predictor variables, I should say, if we use no predictor variables, and if someone asks us to make a then our prediction for Y is just going to be the mean of Y, okay, which is 5. Y bar equals 5. And so what we have is the total sum of squares. What color do I want to use to represent the total sum of squares? Okay, the total sum of squares is the distance between each of these dots and Y bar. Okay, so the total sum of squares is equal to the sum of the green lines. And so we would get something like this has a distance of 3, so we'd have 3 squared plus 1 squared plus 1 squared plus 3 squared. Okay, so our total sum of squares is 20. Okay, so this deviates from has a distance of 3, has a distance of 1, 1, and 3. Okay. Meanwhile, the RSS is the distance between each value, yi minus y hat sub I squared, okay, is the residuals, okay, distance. So I guess I'll do these in orange, okay, I'll say orange lines. And this is how much our values differ from what our prediction line says it should be, okay? So in some cases, the orange line is much shorter than the green line in this case, and for these dots, the orange line is actually longer than the green line, okay? So that's going to be the residual sum of squares, which I guess I would need to know what the y hats are. Let me come back to R, and do I still have model 1? Okay, yeah, so let's do predicted on model 1. I'm sorry, not predicted, predict on model 1. Okay, so I've got 2.6, 4.2, 5.8, and 7.4. 2.6, what is it? 4.2, 5.8, 7.4, okay? So, so each of these will be, 2 minus 2.6 squared plus the actual value is 6 minus what I predicted, 4.2 squared, plus 4 minus 5.8 squared, plus 8 minus 7.4 squared, okay? Which is actually, I can just do resid on model 1, okay? And that gives me that, and then I could just square all these things. And so that gives me 0.36, 3.24, plus 3.24, plus 0.36. Okay, and what's the sum of all of these? Sum of the squared residuals, 7.2, okay. So there we go. Our TSS is 20, my RSS is 7.2, so this is basically how much improvement I got by using the line, right? So by using the red line, how much, quote, improvement did I get? Now for individual data points, it might not be an improvement, right? So for this data point, using the red line is an improvement, because using the mean, I predicted 5 and the real value was 2, so I had a difference of 3. By using the prediction line, I'm predicting 2.6, so I'm getting an improvement there, okay? Over here for this data point, it's actually not really an improvement, because using the mean, I'm predicting 5 and the actual value is 6, and when I use the line, I'm predicting 4.2, which is actually a worse estimate than before, okay? So individual data points, maybe using the line doesn't improve things, but overall, do we get an improvement? Yes, we went from 20 sum of squares total down to 7.2, okay? Kind of the difference between the actual and kind of what I can predict. And so my R squared value, which is TSS minus RSS over TSS, 20 minus 7.2 divided by 20, what is that? Should be 0.64. 12.8 divided by 20 is 0.64. Okay. Whoa, what happened? Something. Oh, geez. Okay, all right, all right. There we go. 0.64. All right. And, oh dear. As far as simple linear regression goes, this is equal to kind of your R value squared. Okay. And so R squared measures the proportion of variability in Y that can be explained using X, okay? So the total variability in Y is given by this TSS, just here's the mean and the values, how much do the values deviate from the mean, and when you total all of that up, that's your total sum of squared. And by using some predictor variable like X, maybe we can get an improvement, where for on an individual level, maybe it's better, maybe it's not better. But overall, what's kind of the improvement there? It goes down, and how much did it go down by? okay, it went down by 12.8, and 12.8 out of 20 is 64% of the variation. So that's your R squared measure, okay? And as far as our data set with the advertising, okay, as far as this thing went, we were able to kind of explain around 61% of the total variation that exists in all of these dots. So all of these dots vary quite a bit. If we just didn't look at the TV advertising, so that's what we get there. Okay, and for simple linear regression, we see that we can calculate the correlation, which is like the covariance but normalized to kind of account for the standard deviations of each variable. So we get the correlation, and then that R squared is equal to the correlation little r quantity squared for simple linear regression where you're only using one variable there. And then we move on into multiple linear regression, okay? And so multiple linear regression is just an extension of the same idea in that we're going to find linear relationships, straight line relationships between x and y, except now we're going to look at multiple predictors, okay? We're going to not just have TV predicting sales, but we can look at the TV advertising budget plus the radio advertising budget plus the newspaper advertising budget, okay? Each time we're assuming each of these things has a linear relationship, okay? Now, if all you learned was simple linear regression, you might want to do 3 separate simple linear regressions, okay? But you're going to run into some problems if you do that, right? Because a lot of times these predictors don't work entirely independently of each other, and so instead we kind of combine them all together, and this is the form of the multiple linear regression. You've got different x predictors, x1, x2, all the way up through xp. In our case, we've got 3. We've got TV, radio, and newspaper. Okay, so we've got 3 x's, x1, x2, x3, and then each of those has its own coefficient. You've got a b0 and or beta 0, beta 1, beta 2, beta 3, right? And so this is the form of the model that we are going to estimate, and we estimate it in the same way that that we did before. Okay, we're trying to minimize the RSS, the total sum of squares for the residuals. The residual sum of squares, which is just yi minus what you predict. Okay, so again, if this is how we make the prediction, we just take each of our things and we multiply it by our estimated coefficient. How do we do this? And so again, I think in your 100B class, you figured out how to estimate this. I think it's even, we touch upon it in 102A or 102B. And anyway, you get your estimates that are going to minimize all of this stuff, okay? And here is a diagram of what kind of your fitted line or fitted surface might look like. So we can do it for 2 predictor variables and 1 output variable. And so in this case, linear relationships are always going to be lines or planes or hyperplanes. And so so here we can plot it if we've got 2 predictors. We've got an x1 and an x2 and a y. And so we can plot this in 3D. We can't do 4-dimensional plots. That's beyond our mental grasp, I guess. And even this it's a 3D plot, but it's really just a 2-dimensional representation of a 3D concept. I don't know. Okay. Um, but anyway, this is what we do, and kind of the same ideas that exist for simple linear regression exist here as well. Okay, you get your estimate, your coefficient, okay, by minimizing the residual sum of squares, which probably we do via x transpose x inverse x transpose y, or you can do some other approach to minimize them. And again, every coefficient, every value that we're estimating based on our sample, every statistic has its own sampling distribution, which means it has a standard deviation and standard error. And we can calculate the test statistic for each of these things. And when we do that, we can get p-values, and we find that when we did our analysis, we get significant values for TV and radio, but not for newspaper, okay? And interestingly enough, the coefficient that we estimate for the newspaper is actually negative 0.001, which would seem to us to indicate that increasing spending money on the newspaper advertising actually decreases our sales numbers, which would be problematic. But if we look at it, this tells us that this value of negative 0.001 is actually not significantly different from 0 as far as as far as this goes, okay? And so, the question, if we did this individually, okay? So if we go back, let me just pull up this other slide here, okay? If we look at the newspaper thing, though, and we did simple linear regression where we just look at sales versus newspaper, we would definitely get a positive slope, and we would definitely get some kind of relationship in the thing. And I think, and so here they did simple linear regression here, and it comes out to, have a significant effect. But then when we considered all of the variables all at once in multiple linear regression, we're getting basically no effect, okay? And so here's the question. Does it make sense that for the multiple linear regression to suggest no relationship between sales and newspaper, while the simple linear regression implies the opposite, okay? So is that all right? Okay, and it says it does make sense. It says if we look at the correlation matrix for the 3 predictor variables displayed in table 3.5, where is right here, okay? So here's the correlation, and we're asking, okay, what's the correlation between TV and radio, TV and newspaper, and radio and newspaper, and stuff like that, okay? It says, notice that there's a correlation between radio and newspaper of positive 0.35. This says that when we spend more on newspaper advertising, we're also at the same time spending more on radio advertising, okay? And so let's just assume, that the multiple linear regression is correct in that the newspaper advertising has no impact on sales, but the radio advertising does have an impact on sales. And so in the markets where we do spend more on radio, there's going to be more sales. And because there's correlation between radio spending and newspaper spending, we're also going to see, we're going to end up seeing a relationship where it looks like there's a positive relationship between newspaper spending and the sales numbers. Okay? So what this is saying is that because radio and newspaper have a positive correlation, when I spend more on radio, I also happen to be spending more on the newspaper. So even if newspaper has no effect on the sales, because the radio spending and the newspaper spending kind of go together, if really it's only the radio that's impacting the sales, when in markets where I'm spending more on the radio, I'm going to see increased sales, and that could lead us to believe that newspaper is related to increased sales, because in those markets I also happen to be spending more on the newspaper sales, right? So does that kind of make sense? So we're saying that multiple linear regression helps us kind of try to disentangle some of these things, but of course it's difficult to, because in our data everything is kind of tied together, right? It's difficult to fully disentangle the effect of each predictor variable. Okay, and this is this is a problem, right? So yeah, it comes away and it says newspaper sales are a surrogate for radio advertising, meaning that when radio advertising goes up, newspaper advertising is also going up. And so if we looked at just the relationship between sales and newspaper spending, it's going to look like newspapers getting credit for the increase in sales, but really it's just that the radio sales are impacting the thing. Okay, and this is just kind of and here they give us silly examples, okay, for real potentially real life situations, right? So if you did a regression on shark attacks and ice cream sales for at the beach, you would see a positive relationship between shark attacks and ice cream sales, and of course it's not that ice cream sales is increasing shark attacks, but really it's higher temperatures cause more people to visit the beach, and more people visiting the beach will lead to more ice cream sales and more shark attacks. Shark attacks is such a bad thing, because I mean, how often do they even happen, right? And it's usually, okay, well, anyway. So anyway, but anyway, we've got that, right? And so rather than doing simple linear regression separately, where you're not going to be able to pick out kind of these interrelated things, it's better to do the multiple linear regression and stuff, okay? And when you do multiple linear regression, however, okay, the null and alternative hypothesis, and I don't know if everybody realizes this, is that your null hypothesis is that all your coefficients are 0, and the alternative is that at least one is not 0, okay? And you get your global F statistic, which is calculated. And your global F statistic, generally, for any large data set, your global F statistic will almost always, not almost always, but generally for any large data set, you're going to get a p-value for your global F generally close to 0, okay? And that's because the null hypothesis is saying that all of your predictors are 0, okay? And usually at least one of your predictors is related to the output, right? If you've got an interesting data set, at least one of your predictors is usually related to the output. And so so this is what you're testing, and so this is you're almost always gonna reject this null hypothesis, because if at least one of them is not 0, this is going to turn out to be significant, okay? And so where did I go? Okay, so so when we did that, we get an F statistic of 570. Rule of thumb F statistics greater than 4 are significant. So rule of thumbs is what? T's greater than 2 or more negative than negative 2 are significant, and F's bigger than 4 or more negative. No, F's can't be negative. So F's bigger than 4 are significant. General rule of thumb. Okay? And here we're getting an F of 570, so it's very significant. Okay? And this is just saying kind of your expected values for this end up being kind of close to the end up being the variance. Okay. Okay. And so here it says the null hypothesis is this, is that everything is 0. And your appropriate F statistic is this. Okay, one issue that that we can run into, though, okay, is, you know, how do we decide on the variables? Okay, so when we're talking about variable selection, you know, let's say we have 2 variables, right? We have technically 4 models to pick, right? A model containing none of the variables, a model containing only x1, one that contains only x2, and a model containing both x1 and x2, all right? So we can look at all 4 and determine which one's the best. And we've got different statistics. You've got your AIC and your BIC and your adjusted R-squared, which we'll talk about in chapter 6. But if you've got more than 2 variables, then there's, you know, 2 to the p models to be considered, right? So if you've got 3 variables, now you've got 8 different models, and if you've got 4 variables, you've got 16 different models. And so this becomes very impractical in terms of like testing out every single possible model to see which one is the best, right? And so probably in your 101A class, you talked about a few different strategies for selecting the variables to use, okay? And so one is forward selection, where you start off with the empty model where you have no predictors and you add variables one at a time, picking the one with kind of the one that's going to result in the lowest RSS, and then you keep doing that, keep adding until some kind of stopping criterion. And then the other is backward selection, where you start off with all the variables and then you delete you know, your least significant variables one at a time. And then you've got kind of got this forward and backwards, where you keep going forward, and then as soon as something becomes insignificant, you delete it, and then you go back and forth and something like that. And so those are some strategies. There are pros and cons to those strategies, and sometimes when you use forward selection or kind of this mixed selection, you can end up, you know, maybe not picking the best set of variables, but it often gets you close to a good set, okay? And I think that's something that we have to accept as statisticians, is that we might not always get the best, okay? But if we get something that's good enough, then we're happy, okay? This is our life, okay? We're just shooting for good enough. Okay. All right. When we do multiple linear regression, okay, we want to know what is your R-squared value, okay? Your R-squared value can also be equal or be calculated by finding the correlation between the actual values and what your model predicts, your y hats. It's a correlation between y and y hat, okay? And so, you know, when you are plotting, when you're trying to plot more than two variables, right? So when you have two variables, you can kind of plot this three-dimensional surface, but when you got more than this, you can't really plot a surface or a hyperplane like this. But you can plot the fitted versus the actual, okay? And if the fitted values and the actual values align quite closely, you're going to have a high correlation, and this means your multiple linear regression does do a good job. So, does explain a lot of the variance, okay? So an R-squared value that is close to 1 indicates that the model explains a large proportion of the variance in y, okay? So you're a large R-squared, okay? But one of the issues is that R-squared will always go up if you add more variables, okay? If you add another variable, you're going to be able to explain a little bit more variance, okay? Because usually you can find like even just the slightest pattern in something, right? You know, you're trying to predict how much money somebody's going to spend at the store, and let's say you've gathered all sorts of variables, okay? And maybe the significant variables are things like I don't know, whatever displays and stuff you have and how much money was in the person's pocket. But then if you collected other variables, maybe just in your random data set, it turns out that the people with brown hair spent a little bit more money than the people with blonde hair, and that the people with blue eyes spent less than the people with green eyes, or something like that, okay? Who knows, right? But you're just saying, like, let's keep adding these variables into our data set, and just for your data set, they happen to explain a little bit more variation. And you can keep adding this, but should you be doing this? No, probably not, right? And this is an issue with R-squared. So with R-squared, it's just talking about the proportion of variation explained, and it doesn't really account for how many variables have been used in the data set or in the model. And so relying solely on R-squared as a measure of how good a model is can get you into trouble, because then if you're going to say maximize the R-squared, I just want the biggest R-squared possible, you're going to end up including a bunch of variables that probably should not be included, right? And so you have a few other values. You've got the you have the RSE, okay? To kind of measure, take into account how many predictors that you are using, okay? And so if you use a ton of predictors, this value, 1 over n minus p, this is going to get smaller, and so this is going to end up getting bigger, right? So so RSE will increase even though your given that the RSS decreases and stuff. Okay. So using solely the R-squared is may not be the best. Okay. as far as making predictions go, okay, all we do is we just plug in our x values into our model to get kind of your predicted value, your y hats, and then you can kind of create a confidence interval, and we're assuming that our linear model is a reasonable approximation for life. Okay, if it's not a linear model, then we can get into trouble here. Okay. Okay, and then the last part is just some other stuff to consider. And so one thing that we often have to deal with is using categorical variables, or here we call them qualitative predictors. Okay, and so a lot of times to do this, we will have to code our categorical variables into things like zeros and ones. Okay, or making kind of dummy variables. So here we have gender, and we can say male 0 is 0 and female is 1. Okay, and basically the prediction for male is going to end up being beta 0, and if it's female, it's going to be beta 0 plus beta 1. Okay, because our model is beta 0 plus beta 1 times x sub I, and x sub I is 0 or 1. Okay, if you have more than two categories, you can't just use 0 and 1, and so you end up having to have one value for each kind of each category. Okay, so here we've got three categories. We've got African American, Caucasian, and Asian. Okay, and so the way this is going to work is that if the person is African American in this data set, their x1 variable will be 0 and their x2 variable will be 0. Okay, if the person is Asian, they will have a 1 for x1 and a 0 for x2, and if the person's Caucasian, they're going to have a 0 for x1 and a 1 for x2. Okay, so you're never going to have somebody with both an x1 and an x2. Okay, at least in this data set. Okay, we're assuming each category is separate and that there's no overlap. I mean, technically you can have people who are mixed races and things like that, but at least in this data set, every category is separate and there's no overlap, and so each person just gets a 0, gets a 1 in only one of the variables and zeros in the others, or in this case, if they're the default race or ethnic group is African American, and so that they have a 0 for both x1 and x2. And in this case, it gets coded up like this. Basically, if the estimate for the person being Asian is this, the estimate for the person being Caucasian is this, and the estimate for African American is this. Okay, so that's how categorical variables are handled in a linear regression setting, where each of these things get coded into variables of zeros and ones. And so you can see, if you have a data set where you have something like 50 possible categories, you're going to end up having like 49 columns of variables to when you kind of encode these as zeros and ones. Okay, this is often called one-hot encoding, because everything's going to be a 0 except for one of those columns, and that's going to be the one that is quote hot, which will get a 1. So you don't have more than one. That's a 1. It's all zeros, and one value is a 1 based on each category. And so this can, depending on how many categories you have, you can end up having a bunch of x variables. And keep in mind, every x variable that you include has its own beta to estimate, which is going to eat up a degree of freedom, right? So if you, depending on how many observations you have, you might end up, quote, eating up a bunch of degrees of freedom to degrees of freedoms for every parameter that you need to estimate. And so sometimes it's better to just kind of group a bunch of the categories together and there's always assumptions that you're making when you do that, right? So, so if we're talking about like race, a lot of times you'll have different racial groups, and this is always a topic that's sensitive and difficult, because how do you group people together, and how many groups should exist, right? So in the census form they might say, like, what's your race or ethnicity, and you can have white and African American, or black or Asian and things, and then should you further split Asian into East Asian and South Asian and Southeast Asian? Should you further split that up into Chinese, Korean, Japanese, and who knows, right? You can keep splitting these up, right? And even among China, you can split those up into Han and I don't know, the different ethnic groups in China and stuff like that. How many things should you split these things up into? If you're gonna make an other, who's being categorized as other? Doesn't it? It's messy, right? Because things are not clean cut, right? I don't know if this is true. I read something about Genghis Khan and how he was so, anyway, like, I guess a bunch of the world carries Genghis Khan's DNA. So anyway, so this is how things for categorical variables get coded up. We can, we've been talking about the linear model. A lot of this can be extended, and you can include an interaction effect, right? By having something where x1 and x2 are related, right? So is there an interaction between these two variables such that when x1 increases and x2 decreases or increases, like, do they have an even greater effect or something? And so you have interaction terms. And that might be different from just the purely additive assumption where x1 increases by this much and x2 increases this much. Maybe if both of them are increasing together, they have an even greater effect, or maybe they counteract each other, and they end up eliminating each other. Okay, so that happens with the interaction effects. Okay, and so here, if we look at, in this case, it's not a huge, but it is a significant thing. So we're looking at the effect of TV and radio, and TV and radio, and it turns out that more TV spending increases sales, more radio spending increases sales, and TV and radio also seem to be working together, such that an increase in TV adds up 0.019, and an increase in radio adds 0.0289. But that when you use them both together, they increase even more than what you might anticipate from them independently working. Okay, and so here they call this like a synergy of the advertising. We call this an interaction effect, and sometimes the opposite happens, where if you increase one variable, it goes up, and you increase the other variable, it goes up. But when you increase them both together, the resulting effect is smaller than what you would have expected, and maybe there's like a negative interaction between the two there. Okay. Okay, and I think that's that. Nonlinear relationships, we'll take a look at this some more in the future, but you can easily just take one of the variables and square them, or make them polynomials and things like that, and create models based on that. Okay, and then this points out a bunch of problems, and I think this should have been emphasized very strongly in your 101A class, where you've got nonlinearity, correlation of the error terms. You want to see even correlation, purely random, that there's no additional pattern that you can see, your error terms and things like that. And then the outliers and high leverage points can strongly influence your estimates there. So watch out for that. Okay, we'll end here for today, and I will assign some homework from chapters 2 and chapter 3, and I'll make that due next week. And then we'll see you guys on Monday. And then in your discussion section today, your TA will work through kind of the lab in chapter 3, going through all of this. And I think they did this in chapter 2. She did not use attach, right? She said don't use attach. Was that even mentioned? Okay, all right. So one thing, our textbook uses the function attach, but our strong emphasis is don't use attach, because that inserts your data set into the search path, and that just messes everything up. So don't use attach. Okay, anyway. All right, we'll end there. We'll see you guys next week. Have a good week.